Hello everyone and welcome to A+ Physics. I'm Dan Fullerton, and in this video we're going to go over the solutions to the AP Physics 2 exam, the free response questions from the year 2016. Now as we go over these, I want to let you know in advance the College Board has not yet released their scoring guide as I'm making this video. So quite possible, even probable, I miss a point or two with some of the minor details, but I think this will at least give you a good idea how you would go about tackling these sorts of questions. So with that, why don't we dive into question 1. If you don't have it, you'll find a link to the exam in the notes below the video. But it looks like this is a thermodynamics problem, so we'll start there. It says we've got 2 moles of a monatomic ideal gas. There's a piston on it, and the piston's movable. The gas is taken through the thermodynamic cycle shown on the PV diagram, and it gives us the area of that piston. Question 1 says calculate the force that the gas exerts on the piston in state A. Well, that should be pretty straightforward. We'll start by listing what we know. We know pressure at state A is 10 to the 5th pascals, right from the diagram. We also know the area given in the problem is 5 times 10 to the minus 3 meters squared. So putting those together, I know that pressure is force divided by area. Therefore, force is pressure times area, or 10 to the 5th pascals, times our area of 5 times 10 to the minus 3 square meters, gives me a force of 500 newtons. Not so bad to start out with. Then it says, explain how the collisions of the gas atoms with the piston allow the gas to exert a force on the piston. That's kind of a wide open question, but I'm betting they're probably looking for something around the lines of talking about momentum transfers. So I would answer this something like, as the gas atoms collide with the piston, they transfer momentum to the piston over a short time interval. This results in a force on the piston consistent with the impulse momentum theorem, or change in momentum delta P is force times delta T. And I think that would sufficiently answer A1. Now for A2, it's asking us to calculate the temperature of the gas in state B and indicate the microscopic property of the gas that is characterized by the temperature. All right, well, we can use the ideal gas law to find the temperature in state B. So this will be A part 2. We can use the ideal gas law, PV equals nRT. Therefore, the temperature at B is going to be the pressure at point B times the volume at B divided by nR. Pressure at B is 10 to the 5th pascals. Volume at B, 0.1 cubic meter. N, we've got 2 moles of gas, and then our gas constant, 8.31 joules per mole Kelvin. Run that through my calculator, and I come up with about 602 kelvins. The microscopic property of the gas characterized by temperature? Well, the average kinetic energy of the gas molecules is characterized by temperature. So I would state average kinetic energy of the gas molecules, and I think you're covered there for part A2. Now let's take a look at B. It's asking us to predict qualitatively how the internal energy of the gas changes as it is taken from state A to state B and justify your predictions. Well, although it says to do it qualitatively, what I'm probably going to do is solve it quantitatively, numerically, see what happens, and then I'll answer the question. And I'll use my numeric calculation to justify my qualitative explanation. So I would use the ideal gas law again, and let's find the temperature at A first using this formula. Temperature at A must be pressure at A, volume at A, divided by nR. Pressure at A, still 10 to the 5th pascals, but the volume at A we had as 0.04 cubic meters, divided by nR, 2 times 8.31 joules per mole Kelvin. Run that through the calculator, come up with right around 241 kelvins. All right, so what happens? We've got a temperature increase as you go from A to B. So T increases as you go from A to B. Therefore, the internal energy increases. You might put a few more words around that, but the general idea, if you have the same amount of gas and maintain the same pressure while increasing the volume, the average kinetic energy of the gas molecules must have increased. Therefore, internal energy is increasing. And that should probably cover you pretty well for part B1. For part B2, now it's asking us to calculate the energy added to the gas by heating as it is taken from A to C along that path ABC. All right, a little bit more calculating to do here, but let's start off by finding the work done as we go from A to B. That's going to be the area under that graph. So the work going from A to B, we've got the area, which will be 10 to the 5th pascals times 0.04 cubic meters minus 10 to the 5th pascals times 0.1 cubic meters, which is going to be 10 to the 5th times 0.06, or negative 6,000 joules. Going from B to C, there's no change in the area of the graph, the area under the graph. It's a vertical line, so the work done there is 0. So we know the work going from A to C must be negative 6,000 joules. Little bit more to do here, though. We also need to then characterize the change in the internal energy, which is going to be the internal energy at C minus the internal energy at A. And the way I do that is, well, I'm going to go to the next page and give ourselves a little bit more room here. So as we go to the next page, I would state first, we know the internal energy at A, 3/2 nR times the temperature at A. And in a similar fashion, the internal energy at C is 3/2 nR times the temperature at C. Well, we know the internal energy at A, or can find that pretty easily. The internal energy at C, well, we need to find the temperature at C in order to go through and solve this correctly. So I would find temperature at C using the same formula we've been using, PV over nR from the ideal gas law. That'll be 0.5 times 10 to the 5th pascals times our volume at C, 0.1 meter cubed, all over 2 times 8.31 joules per mole Kelvin, or about 301 K. So since it's really delta U that we're after, and I stated that incorrectly a minute before, we don't need to know these exactly, we just need to find the difference. Delta U, our change in internal energy between A and C, is going to be the internal energy at C, not equal to, the internal energy at C minus the internal energy at A, which will just be 3/2 nR times the temperature at C minus the temperature at A, which is 3/2 nR. Temperature at C minus the temperature at A, while C was 301 K, temperature at A was 241 K, that's a difference of 60 K, is going to give us 1,500 joules. So we had negative 6,000 joules. The change in energy going from C to A is 1,500 joules. With that, we can go to our law of thermodynamics. Delta U equals Q plus W, heat added to plus work done on. We're looking for the heat, so Q is going to be equal to delta U minus W. Our delta U, change in internal energy, 1,500 joules, minus work done on of negative 6,000 joules, gives us 7,500 joules. So a little bit more involved there for part B2, but I think we've answered it sufficiently there with the energy added to the gas by heating must have been 7,500 joules. Finally, we get to part 1C. Oops, my screen's sliding around on me. And it's doing it again. I don't know why. 1C. Okay. Determine the change in the total kinetic energy of the gas atoms as the gas is taken directly from state C to state A. Well, the total change in kinetic energy of the gas atoms must be negative 1,500 joules, consistent with part B2. We really already calculated that. So that's going to be negative 1,500 joules. And it doesn't ask for a justification in any more detail than that. So I don't think we have to go into that in any detail, especially on a timed test. I'd say that would sufficiently answer question 1. So with that, we'll take a short break and we'll come back to question 2. All right, and we're back now with question 2. This question's fairly open-ended, and I'm going to answer this a little bit differently than I normally do. So I'm going to show a video that's going to go through a lot of parts A and B separately, because I think the illustration of the video better explains the procedure you would use than me trying to write it out in words, which would be extremely boring here. And then we'll get into more detail on C and D. So it starts out by telling you you're given a glass block specially treated so that light can be seen as it travels through the glass. The student is asked to design an experiment to measure the index of refraction of the glass, and the light source available in the laboratory is a hydrogen lamp that emits red light of a known wavelength. So it's not a helium neon laser, a typical red laser that you'd probably see in most classes. It's a hydrogen lamp emitting red light. That might throw you off a little bit if you don't catch it. So, part A, a linear graph is to be used to determine the index of refraction of the glass. Indicate the quantities that should be graphed and describe how the graph could be used to determine the index of refraction. All right, we'll do that in the video. And then outline an experimental procedure that would gather the necessary data. Include sufficient detail that someone else could follow that procedure, and use typical laboratory classroom equipment. We'll do that in the video too, but the one thing I'd note here, since we're given a hydrogen lamp with red light, what you would need to do is somehow form that hydrogen lamp's red light into a beam. A couple ways you could do that. You could put it at the focus point of a converging lens to get a beam out of it, and then use some sort of aperture, piece of cardboard with the hole in the middle to make sure you've got a nice slim beam. You could put the lamp inside a parabolic mirror to form a beam. You could use just the lamp itself and maybe use the cardboard and hope you had enough brightness to get a beam. But in all honesty, if you're using typical classroom laboratory equipment, what I'd do myself, probably not the right answer for the exam, is I'd throw away the hydrogen lamp and use the helium neon laser instead, because those are cheap, they're everywhere, and work so much more easily, more straightforward. But with that, let's show the video. That'll get us through A and B, and then we'll come back and we will do part C here together. We'll start out with our light beam and we'll watch it as it goes and it enters into the glass, refracting toward the normal and then away from the normal as it leaves the glass block. So there's our light beam. What we'll do once we have that is we'll take our pen or pencil and we'll mark a couple dots on the light beam. We'll mark one where our beam starts. We'll mark one where our beam enters the block, making sure we have a piece of paper under all of this, of course. We'll mark another dot at the exit point of the block, and a final dot further on along the beam. At this point, we'll also draw a horizontal line at the interface between the block and the air at both the entrance and exit points. So we'll draw a horizontal line here, and we'll draw another horizontal line at the exit interface. Now we can get our beam and block out of the way so we can do a little bit more manipulation of everything here. The beam doesn't have to be there anymore. We've got our points. All we have to do now is connect the dots. And we have the path of our beam again. And at this point, we can even erase our dots. We really don't need those any further. But what we do need to do is draw a normal line at these interfaces. So we'll draw a normal line, perpendicular 90-degree line to the entry interface. And we'll do the same thing at the exit interface. So there we have our normal lines. Next, I'm going to label the incident angle theta 1. Theta 2 is the refracted angle in the glass. So we have those labeled. We can measure those with the protractor and record them. We'll also do the same sort of thing at the exit interface. In this case, though, I'm going to call theta 1 the refracted angle and theta 2 the incident angle. And the reason I'm doing that is this allows me to get two data points for the same entry angle. So theta 2 on the at the top when it enters is going to be the same as theta 2 on the way out. We get two data points for the same angle of incidence, for the same experimental setup, to help reduce measurement error. So I've recorded those angles. Next, it's time to start looking at putting all of this in a table. So I'll make a table of theta 1 and theta 2 using the average of the entrance and exit portions so they get a little bit better data. And I can do this for angles anywhere from 0 up to, let's say, 80 degrees in 10-degree increments. So I'll get a nice table of theta 1s and theta 2s, and I can then apply Snell's law. N1 sine theta 1 equals N2 sine theta 2. N1, the air side, is equal to 1. The index of refraction of air is 1, so we can replace N1 with 1. And 1 sine theta 1 is just sine theta 1. So that formula simplifies a little bit. And now I'm going to rearrange this to solve for N2. N2 must be sine theta 1 over theta 2. Now that we have our index of refraction, what I can do is I can then plot sine theta 1 on my y-axis and sine theta 2 on my x-axis. As I plot my points, I should see a fairly linear trend, and I can draw my best fit line on my graph, and then I can take the slope of that line. My rise divided by my run gives me my slope, which is sine theta 1 over sine theta 2. So the slope of that line should give me N2. There's the index of refraction of the glass. Okay, so now we're back here with part C. Predict how the path of the light will change as it enters the glass. Support your prediction using a qualitative comparison of the speed of light in glass and the speed of light in air. And what I would state for this sort of question is that as the light enters the glass, a slower medium with the higher index of refraction than air, it will be refracted toward the normal. This occurs because the portion of the wavefront first entering the glass will slow down before the portion of the wavefront later entering the glass. And I think that would qualitatively explain that one. Now for part D, another fairly open-ended question. Describe the process or processes by which red light from the lamp is produced by hydrogen atoms initially in the ground state. So we're explaining how we get red light from this gas discharge lamp. Draw and label an energy level diagram that supports the atomic processes you describe. You could probably write pages on this. However, this one's kind of tough to know where to stop. So I'm going to go into what I think is probably a little bit more detail than you need of what I would do, and make sure you hit all the points they're looking for. But in all honesty, I'm expecting the scoring guide to require you to do a little bit less than what we have here when that comes out. So the first thing I do is recognize that electrons in the hydrogen atom initially in the ground state are excited to a higher energy level, typically by applying an electric potential difference. The electrons then relax, they fall down to a lower energy state, and when they do this, they release a photon with energy exactly equal to the difference in electron energy levels. So if we were to draw an energy level diagram for hydrogen, and I'm not going to put all the lines in, we have some lines up here, that's ionization at the top, something like this. Down here we'll have n equals 1 ground state, n equals 2, n equals 3, n equals 4, and so on. And the energy levels over here, well, this is probably going further than you need to for the problem, but just in case, you can calculate those. It's equal to negative E naught over n squared, the level squared, where E naught is negative 13.6 eV in this model of the hydrogen atom. So at the first energy level, we've got negative 13.6 eV over 1 squared. That must be negative 13.6 eV. The second energy level will be negative 13.6 eV over 2 squared, or 4, which is about negative 3.4 eV. And our third energy level is negative 13.6 eV over 3 squared, or 9, or negative 1.51 electron volts. So then, what would happen? Well, if we have an electron in the ground state, it gets excited somehow to the n equals 3 state, applying a voltage. Once it's at the 3 state, it falls down to 2, giving off a photon, and then it'll fall down to 1, eventually giving off another photon. The energy of that photon, if we focus on this second step, this photon, the energy of that photon is equal to the initial energy level minus the final energy level. In this case, that's going to be negative 1.51 eV minus negative 3.4 eV, or the energy of that photon is 1.89 eV. We can find the wavelength of that photon, wavelength, Planck's constant times the speed of light, divided by its energy. And if I write hc in terms of eV nanometers, I just happen to remember that that's 1242 eV nanometers. I can leave my energy down here in eV and get an answer for the wavelength in nanometers, about 657 nanometers, which is a red photon. So just to summarize there, red light produced by an electron relaxing from the n equals 3 to the n equals 2 state emits a photon with energy 1.89 eV, corresponding to a wavelength of 657 nanometers, which is red light. So that's how you get the red light from the lamp. So I would think this should be more than sufficient, along with a couple sentences of what's going on, to answer 2D. Understanding, of course, that you could go into much more detail and probably even get away with a little bit less. I would be mighty surprised if they required you to calculate the exact energy levels, and instead we're looking for the fact that an electron is excited to a higher energy level by a voltage, and as it falls down to a lower energy level, it gives off photons of a specific energy, this energy corresponding to red light. And that should answer us pretty well for step 2. Great place to stop for a second, and we'll move on to step 3, to problem 3, excuse me. Our electrostatics question, number 3. The dots in the figure above represent two identical spheres, x and y, fixed in place with their centers in the plane of the page. They're both charged, and the charge on sphere y is positive. So we know y is positive. The lines are isolines of electric potential, or equipotential lines, in the plane of the page, difference of 10 volts between each set of lines. The absolute value of the electric potential of the outermost line is 50 volts. Indicate the value of the potentials, including the signs, at the labeled points A and B. So for 3A, I would look at that, and as we count off the lines, we know y is positive. So based on the shapes there, I can conclude that we're going, and 50 volts is the magnitude of the outermost one. A must be 60 volts. And B, 2 more lines in, must be 80 volts. So that'll bring us into something a little bit more in depth. 3B. How do the magnitudes and the signs of the charges of the spheres compare? Explain your answer in terms of the isolines of electric potential. Well, based on the shape of those lines, I conclude that both spheres are positively charged, as you can see within the shaped equipotential lines of 50, 60, 70 volts. If they were oppositely charged, you would see something like our charged on the left, looking kind of like that, and you would have some sort of barrier line as you went over to the ones on the right. That's not what you have, however. Instead, you have that somewhat elliptical shape where it's sharing that equipotential line, and that's what tells you that they're both positively charged. Now, as we look at this as well, how do the magnitudes and the signs of the charges of the sphere, we have to look at the magnitudes. You could say pretty easily that the charge on y is greater than the charge on x. Why do you know that? Well, if V equals kq over R, Q equals the voltage times R over K. So for the same voltage, say you look at the 70 volt equipotential line, Ry is greater than Rk, therefore Qy is greater than Qx, or Ry is greater than Rx, excuse me, therefore Qy is greater than Qx. You look at the radii, the difference in the voltage as you go out from those spheres, and based on that you can tell that you have the greater charge on Y. So then, B2. The spheres have masses in the same ratio as the magnitudes of their charge. The isolines of gravitational potential have shapes similar to the equipotential lines. Why do they have similar shapes? Well, both electric potential and gravitational potential energy follow an inverse relationship with R. The electric potential energy is going to be K Q1 Q2 over R. The gravitational potential energy is G M1 M2 over R. So they both have the same relationship with respect to R. You would expect to have the same shape of the lines. And that, I think, will get us through B2. Let's get us some more space as we look at part C. For part C over here now, it says the potentials at the three labeled points VA, VB, and VC, a proton with charge plus Q and mass m is released from rest at point B. Describe one similarity and one difference between the electric and gravitational forces exerted on the proton by the system of two spheres. The similarity and difference you describe must not be one that generally apply to all forces. Fairly open-ended, and you're kind of guessing at what they want you to write here. But I would say something around the lines of, the proton's going to experience an electrical force toward A compared to a gravitational force toward C, since gravity only attracts. The big difference here is the direction of the force between gravity and electricity. In both cases, the magnitude of the force, though, is proportional to the inverse of the square of the distance. So the similarity is that inverse relationship with the distance between your quantities. So there's your similarity. And something like that, I think, should adequately answer that question. Now we come to part D. At some point, after being released from rest at point B, the proton is moved through a potential difference of magnitude 20 volts. Find the change in electric potential energy of the proton sphere's system when the proton is moved through the 20 volt potential difference, and answer in terms of those quantities and physical constants. Well, the way I'd look at this one, we're looking at the change in electric potential energy. Delta U is going to be minus Q delta V, or minus 20 volts times Q. Well, we could just write minus 20 V times Q. And I think that answers the question just fine for D1. For part D2, now, as it's moved through the 20 volt potential difference, the proton was displaced a distance d by the electric force. Determine a symbolic expression for the total work done on the proton by the electric field in terms of the average magnitude E average of the electric field over that distance. Well, force is charge times electric field, and work is force times distance, so the work would be Q times our average electric field strength times that distance. That's simple, and I think you're good with part D2. D3. We've got a couple statements here discussing the kinetic energy of the proton, and they want to know about each student's claims, whether it's correct or incorrect, and discuss. Well, student 1 says if the system is defined as the proton and the spheres, the increase in the proton's kinetic energy is due to a change in the system's potential energy as the proton moves through that 20 volt potential difference. I'd say that's correct. That claim is true as the total energy of the system stays constant. If the proton's kinetic energy is increasing, the system's potential energy must be decreasing, consistent with the law of conservation of mechanical energy. Student 2 says the system is defined as only the proton. The kinetic energy of the proton increases because work is done on the proton, positive work, by the electric field. I'd say that's also true. As you're looking at the proton, as work is done by an external force on the proton, energy is added to the proton, to the system, which in the case is a form of the proton's kinetic energy. So I'd say both of those are true. And that's kind of a long question, but that should finish us up on number 3. Quick break, and we'll come back with our fourth and final question. All right, we're back with our fourth and final question on the AP Physics 2 2016 free response. Some students are investigating the behavior of a circuit with 4 components in series: a resistor of resistance R, a capacitor of capacitance, you guessed it, C, a battery with potential difference E, and a switch. Initially, the capacitor is uncharged and the switch is open. A says determine the current in the resistor and the potential difference across the capacitor immediately after the switch is closed. Well, I'm first going to draw my circuit. As I look at this, I'm probably going to draw it something like this. We've got our battery, our source of potential difference. We've got a switch. We've got a resistor R. And we've got a capacitor all in series. There we go. And for A1, at this point, when it's first turned on, the capacitor acts like a wire at some time before that switch is closed. Or right after the switch is closed. Before that, it's acting like a wire. So initially, when it's first closed, it's just a wire. So we can pretend all we have is the battery, the resistor in the circuit, and everything else is just closed wires. The current then is just going to be V over R by Ohm's law. Our voltage is the EMF supplied by the battery. The capacitance is charge over voltage, therefore the voltage across our capacitor is Q over C. And initially, Q is 0, therefore the voltage across the capacitor is 0. All of the voltage is dropped across the resistor, which is why you have that full current across the resistor. Now, part 2 says determine the current in the resistor a long time after the switch is closed. So we're assuming at this point the capacitor is fully charged. And at that point, the capacitor acts like an open as t approaches infinity. So at that point, if we treat it like an open, it's fully charged, there's no current flowing in the circuit, and all of the potential difference of the battery is across the capacitor. No current flowing through the resistor, therefore the voltage across it must be 0. So I think that answers part A pretty well. Yeah, that allows us to go on to part B. The switch is opened, the capacitor is discharged, and a second identical capacitor is added to the circuit in series with the other components. The switch is then closed again. So now we've got a similar looking circuit, battery, switch, R, and 2 capacitors in series. Well, the first thing I'm going to recognize is 2 capacitors in series. The equivalent capacitance of those 2 is going to be C over 2. Capacitors in series combine like resistors in parallel. So you could run through the calculations, but that's one I've done enough that I don't have to run through the actual calculation. Lots of places and different ways to do that. Now, let's see. The question: a long time after it's closed, the energy stored in the single capacitor in the original circuit is U1. So if we had U1 up here in our original circuit, that would be U1 is 1/2 CV squared, which in this case would be 1/2 CE squared. That's our U1. Now down here in 4B, it wants to know the ratio of U1, the initial capacitance in this first circuit, compared to what we have with the energy stored in the 2 capacitors in the new circuit, which we're calling U2. Well, let's see here. U2 then is going to be 1/2 CV squared. Our C now, our C equivalent is C over 2, and we've still got our same source of potential difference. So that's going to be CE squared over 4. So the ratio of those two then is U1 over U2. That's going to be 1/2 CE squared over CE squared over 4. 1/2 CE squared over 1/4 CE squared. That's just going to be 2. And I think we've answered part B1 appropriately. B2, the 2 capacitors in series are replaced with a single capacitor that'll have the same energy U2, indicate a plate area and distance between the plates compared to the original capacitors, and show appropriate physics principles to model it. Now, we already said for part B2, the equivalent capacitance is C over 2. Now, our initial capacitance, I'm going to call that C1 up there, is just epsilon naught A over D, assuming an air capacitor. We'll call that A initial, D initial. C2, which is half of that, must be epsilon naught, and if we start with A initial, we need twice the distance between the plates. So I would say you could do this with the same area as the original, but twice the distance will give you half the capacitance. Pardon me. That gets us through part B. I'm going to move to a new page here for part C. All right, part C. The students are then asked to design 2 circuits containing a switch battery and with a small internal resistance, a light bulb, and a capacitor. In arrangement 1, the bulb should gradually light up after the switch is closed, becoming brightest when it's closed for a long time. And in 2, the bulb should be brightest when it's first closed and get dimmer with time. Draw these circuits and justify with a paragraph-length explanation referring to the properties of light bulbs and capacitors and circuits, and the conservation of energy and/or the conservation of charge. That's the tricky part. The justification in terms of conservation of energy and conservation of charge is probably not how I would go about justifying these circuits, but we'll do our best based on the constraints they're giving us in the question. So for part C1, What we want is a circuit in which the bulb gradually lights up. All right, well, let's start with our battery, and we'll give it its little internal resistance. I'm going to put a dash around it, dash line, just to remind me that's all in the battery. We've got our switch, and I'll put the capacitor in parallel with my light bulb. Now, initially, all current flows through the capacitor because it acts like a wire. As it charges, however, more current flows through the bulb as the capacitor acts more like an open circuit until the capacitor is fully charged, in which case this acts like a complete open and all the current goes through the light bulb. So we start with no brightness, then we get all the current through the light bulb. So that should meet the requirements for circuit 1. Now, the justification in terms of conservation of energy and conservation of charge, I'd say something like, in this arrangement, the battery voltage is always equal to the voltage across the capacitor. So as the capacitor charges and the voltage across it increases, the voltage across the bulb also increases. In all cases, the sum of the potential drops around the closed loops equals 0. That's Kirchhoff's voltage law, which is a specific circuits version of the law of conservation of energy. So that's C1. The second arrangement now, in this case, we've got our battery again. We still have our little internal resistance. We'll put our switch over here. Now I'm just going to put my capacitor in series with my light bulb. When the switch is first closed, maximum current flows through the circuit as the capacitor is charged, so you've got maximum current going through the resistor. As it gets closer to its maximum charge in the capacitor, however, the current flow dwindles, eventually stopping when the capacitor is fully charged. So after a long time, there is no current through the bulb. From a conservation of energy standpoint, the potential difference supplied by the battery is matched by the potential drop across the bulb. But as the capacitor is charged, more and more of the total battery supplied voltage is dropped across the capacitor, leaving less potential difference across the resistor until the capacitor is fully charged, with the full EMF of the battery dropped across the capacitor with no potential difference across the bulb, so no current flow through the bulb. Therefore, no light output. Another application of the law of conservation of energy, specifically in this case, Kirchhoff's voltage law, or the loop rule. So I think that answers those questions sufficiently from a conservation of energy standpoint and meets the circuit requirements. So with that, we've completed the 2016 AP Physics 2 free response portion. Thank you so much for your time, everyone, and make it a great day.